Alright, so next we have miscellaneous examples. So this is example 28. Here we have to show that the set of letters in the word cataract and the set of letters in the word tract are the same. So let's just form these two sets. Solution. The set of letters of the word cataract is this. So what we first do, you can see that some of the words are repeated, right, in this, some of the letters are repeated in this word. So without thinking much, you just write all the letters. C A T A R A C T. There is no problem in writing like this because we are allowed to repeat elements in a set. Although repetition doesn't serve any purpose, that's a different thing. But now, because repetition doesn't serve any purpose, so we get rid of the repetitions. So we of course keep C, and after that say A is appearing, and then T is appearing, but then we would not repeat A because we already have A here. Next comes the new word is R, and again we won't repeat A because A has already appeared and C and T also have already appeared. So we just have C, A, T and R. So this is in fact the, for some reason I can't close this bracket, yeah. So this is the set of all the distinct letters in the word cataract. Similarly, the set of letters in the word tract is, let me call this set Y. So here also similarly we first simply write the letters separated by commas and then we get rid of repetitions if there are any. Okay, and this here also we do have T is repeated, right? So we simply write T once and we write the other letters. So are we getting the same set? Yes, of course. T, R, A and C, T, R, A and C. And again, because order does not matter, so these two sets are equal. So X is equal to Y. And in fact, before you write this conclusion, you can, if you want, you can write one more line. Namely, we can see that each element of X is an element of Y and vice versa. That is, each element of Y is also an element of X. So X is equal to Y. So there the solution ends. Next, example 29. In this one, we have to list all the subsets of a given set. List all the subsets of the set consisting of -1, 0 and 1. while discussing the notion of power sets, we already discussed a little bit about how to find all the subsets of a given set. Okay, so that we are going to recall now. See, first of all, without even thinking of anything, you just write the empty set, because the empty set is a subset of every set. The subsets of this are, so first we write the empty set, which is a zero element subset of the given set. There is no element in it. And then you look for the one element subsets of the given set, that is the singleton sets. And there are three. One of them has only 1, another has only 0, and this one has only 1. Oh, this one has only -1, okay. So these are all the one element subsets. And then you look for two element subsets. And again there are 3. 0, 1 and -1, 1. And finally, we look for 3 element subset, which has to be the set itself. Now, can there be 4 element subsets, 5 element subsets? No, because the set itself has only 3 elements. So that's it. That is the list of all subsets of the given set. Note carefully that the example doesn't ask us to find the power set of this set. No, we have been asked to only list the elements of the power set. So there is no need to put further brackets enclosing this list. Okay, that we would have done if the question asked for the power set of this set. Okay, so this is the list. Next, example 30. These miscellaneous examples and the exercises which will come after this, they are more interesting than the usual exercises and examples. Show that A union B equal to A intersection B implies A is equal to B. Because you have union and intersection, it automatically means that A and B are sets. There is no need to mention that separately. So this identity is given. Well, it's not an identity, it's a condition. We have to prove that this is a consequence. Then A and B have to be equal. And whenever you see a claim where you have to prove that two sets are equal, you just have to apply the usual method. You show that each one is a subset of the other. So we start by showing that A is a subset of B. How do we do that? We take an arbitrary element in A, show that that element is also in B. Let A belong to A. In place of small a, see, there is no rule that says that if you have capital A here, you have to take small a. If you want, you can take any other, use any other name, okay, for naming this element. You can call it X or U, whatever you want. Then X also belongs to A union B. Why? Because, oh, see, I have already written X here. Yeah. So A also belongs to A union B. Why? because A belongs to A, so automatically A will belong to A union B. That's because A union B is the set of all elements of A together with all the elements of B, and this is one such element. Since A union B is given to be equal to A intersection B, so we have A in A intersection B. This means that A is in A and also A is in B. Well, A is already in A, that we know because that's how we started our argument, but now A also belongs to B. So we write A belongs to B. So we have shown that any element in A is also an element in B. This implies that A is a subset of B. Similarly, B is a subset of A. And I want you to actually write all the details of this similar part. You take an element of B and follow a similar line of reasoning and obtain the fact that B is a subset of A. Okay, you do this for yourself, for your own understanding. Hence, combining these two containments, we get equality. Okay, so we have proved. Next, example 31. Yeah, this one is also quite interesting. For any sets A and B, show that the power set of A intersection B is equal to the power set of A intersection the power set of B. This may at first look a little confusing, but do not get confused, okay? Here, both the sides have power sets, both the sides of this equation. But again, whatever we have on both sides, they are after all sets, right? So we need to prove that this is a subset of the right hand side and the right hand side is a subset of this. Note one thing, that in many set identities or set equations like this, you go through one side of the argument and write similarly the other side can be done. However, the symmetry may not always be present. This situation is symmetric about A and B. Whatever we did with A here and obtained this conclusion, an exactly similar thing can be done with B and you can obtain that other conclusion. But that is not the case here, because the left hand side is something and the right hand side looks like something else. Okay, the left hand side is simply a power set. The right hand side, however, is the intersection of two power sets. That's why in this solution we have to do both the sides. So let us start by showing that this is a subset of the right hand side. Okay, now you are going to take an arbitrary element of the power set of A intersection B. But what does that mean? What type of elements do power sets have? They have elements which themselves are sets. Okay, so you better take, you use capital letter here. Do not use small letter. Let C belong to PA intersection B. This means what? This means that C is a subset of A intersection B. Why? Because the power set is the set of all subsets of A intersection B. That's why. Then C is a subset of A intersection B. But we know that A intersection B is a subset of A and A intersection B is also a subset of B. This is something we already know. Now C is a subset of A intersection B and A intersection B is a subset of A. Combining these two things, you get that C is a subset of A. Because if C is sitting inside this, which itself is sitting inside this, then automatically C is sitting inside this as a subset. But then C is a subset of A, and similarly combining this and this, we also get that C is a subset of B. But we can express these statements differently also in terms of power sets, in the language of power sets. That is, since C is a subset of A, C is an element in the power set of A. And in place of this, you can write that C is an element in the power set of B. So C belongs to both P of A and P of B. So C will belong to their intersection. Hence, we have thus shown that any element in this, that is the left hand side, is also an element in the right hand side. And that proves that the left hand side is a subset of the right hand side. We have thus proved that P of A intersection B is a subset of P of A intersection P of B. For easy conclusion later, you can give it some numbers, say 1. Next, we prove the reverse containment. Let D be any element in PA intersection PB. Okay, oh, this B is looking like beta. Then D belongs to PA and D belongs to PB. That is, being in PA means D is a subset of A, and being an element in P of B means D is a subset of B. Now you combine these two containments and you get the fact that D is a subset of A intersection B. These imply and so T belongs to the power set of A intersection B. So again, any element in this intersection is also in this set. Hence, PA intersection PB is also a subset of P A intersection B, and say this is 2. From 1 and 2 we get equality. That means we have proved what we wanted to prove. Next comes that type of problem which we have already discussed about in the previous section. So this is example, the so-called practical problems. A market research group what did they do? Conducted a survey of what? 1000 customers and reported that 720 consumers, I wrote customers, almost the same thing but still, okay, 720 consumers like product A. Like product A, and 450 consumers like product B. Product B. What is the least number that must have liked both the products? Least number of consumers, that's understood. That must have liked both the products. Okay, so let's give these sets some name. Let U be the set of 1000 consumers surveyed. Okay. Because the products themselves have been named A and B, we cannot use these letters. Let us just use something else, say x and y, comma, x be the set of consumers who like A, and Y be the set of those who like B. Then the number of elements in U is 1000. The number of elements in X is 720, and the number of elements in Y is, what is the figure, 450. We have to say what is the least possible value of the number of elements in X intersection Y. Now we know that n of X union Y is equal to n of X plus n of Y minus n of X intersection Y, or n of X intersection Y is equal to nx plus ny minus nx union y. Alright, now although we do not know what X union Y is or how many elements it has, but we know something else, namely that in any situation X union Y is a subset of U, because after all we are talking about those 1000 consumers only. So since X union Y is a subset of U, we have the number of elements in X union Y is less than or equal to the number of elements in U. It cannot possibly exceed the number of elements in U. Or if you multiply both sides of this inequality by -1, then the inequality gets reversed according to one of the rules for inequalities. That is, minus of the number of elements in X union Y is greater than or equal to this. Now, on both sides of this last inequality, you can add nx plus ny. Hence, let me write like this: n of X intersection Y. We have already figured out that this is nx plus ny minus nx union y. But this minus of nx union y is greater than or equal to minus nu. So if you replace this by this, then you are possibly writing something less. And that's why inequality like this. Or it may be the same also, because these two may be equal. And that equality case corresponds to the case where X union Y is equal to the set U. But in general, we have inequality. Okay. Some people may be confused as to why I am not continuing to write this inequality. That's because after this line, I am going to write something which should be equal to this. So unless I have a reason to have an even smaller quantity, I don't write inequality here. You see, because of lack of space, we write like this. Generally, we write equations like this, but ideally, it should be in one line. If you write like that, then it will become clear why this should be equal to what I am going to write next. Okay, so nx is what? 720, and ny is 450, and this is 1000. Okay, so let me see if I can do the calculation fairly quickly. Okay, so it should be 170. So we have proved that n of x union y is not necessarily equal to 170, but is greater than or equal to 170. So the least value of nx intersection y should be 170. In other words, at least 170 consumers should like product A as well as product B. You can write that as the last line. I am not writing that. And in fact, this is the thing that was wrong in two of the exercises from the previous exercise set. But anyway, let us see the next one. Example 33. Out of 500 car owners, out of 500 car owners, is it investigated for what? It sounds like they were charged with some kind of something, that they must have done something wrong. The language sounds like that. But anyway, investigated 400 owned car A. Is it a crime to own cars? 200 owned car B and 50 on both. Okay. Both. Okay. Who needs two cars, man? Oh, is the data correct? This is slightly different. Solution. All right. So let us start by naming the sets. Let C1 and C2 be, this time we will write at once, be the sets let C1 and C2 be the sets of people investigated who own cars A and B respectively. Then How many own car A? 400. The number of people owning car B is 200. And those who own cars A and B simultaneously is 50. Then let us calculate the number of elements in the set C1 union C2. Minus C1 intersection C2. Okay, so 400 plus 200 minus 50. So that means 600 minus 50, so 550. No, this cannot be true. This cannot be true because only 500 people were investigated who own some kind of cars. But this calculation indicates that the number of people owning cars, I mean these two, among these two cars, should be actually 550. Okay, or it may have been this number could have been less than 500. In that case, some people would be there in this set of people who were investigated who own neither car A nor car B. Maybe they own something else, some other model. Okay, but this has exceeded the number of people investigated for car ownership. This cannot be true. So that is why the given data is not correct. And this last part, of course, you can write in your own language, however you want to express this inconsistency. Okay, so the conclusion, I leave it to you. You write the conclusion, and because of this, and because there are less number of car owners investigated for ownership of car A and or B, so the given data cannot be correct, it's incorrect. I am stopping here itself. Then, have we reached the last exam? Yeah, this one is a little tricky. Trickier than the other ones. A college awarded 38 medals. Medals in football. But there are more, 15 in basketball, and 20 in cricket. If these medals went to a total of 15 men, and only 3 men, have I got something wrong here? A college awarded 38 medals in football, 15 in basketball, and 20 in cricket. How can it go to a total? Oh, sorry, yeah, 58, okay. Yeah, the figure is wrong here. If these medals went to a total, let me just write that figure. If these medals went to a total of 58. I do remember it should be 58. First, I mistook the figure. I wrote 15 here. 58 men and only 3 men got medals in all the 3 sports. How many received medals? In exactly 2 sports. Okay, now it has to be done in steps. The argument goes like this, see, this is I think the first time that we have to use that formula for the number of elements in a union, but of 3 sets. So far we had to use only the formula for 2 sets, but this time we have to use the formula for 3 sets. Let us first name the sets. Okay. Let football, basketball and cricket denote the sets of men who got medals in football, basketball and cricket. Respectively. All right. Now, what are the things we are given? We are given that 58 of them got medals. So, see, 58 of them got medals. That means they have to play the games, at least one game, and that is why the number of elements in the union of these 3 sets is 58. This is 58. What else is given? The individual numbers are given. 38 got in football. So N of F is 38. 15 in basketball. And how many got in cricket? 20. Something else is also given. Namely, that 3 men got medals in all the 3 sports. That is also given. That is, the intersection of all the sets has 3 elements in it. So let us first, without really thinking much about exactly what we have to find, let us find what we can find with this information. In other words, let us first blindly apply the formula for the number of elements in the union of 3 sets. And from there we will figure out what we can do next. We know that N of F union B union C is n of f plus n of b plus n of c minus, you remember the rule, first plus comes and then minus and then again plus, and this happens alternately until you reach the end. B intersection C minus C intersection F, but then again plus F B C. So we know this is 58. We also know these three, and they are 38, 15 and 20. Plus, actually we also know this is 3, so let me just write that with these things. These three, however, we do not know, this one and this one. FB, BC, FC. So let us calculate this itself. So if you bring all these things to that side, all the minus signs will become plus. See, when we use this kind of language now, bring all these things to that side, actually there is no physical movement, of course. What you are doing is that you are adding this to both sides. So the right hand side no longer has these things because of cancellation. Okay, that way you can cancel, and the left hand side is left with these things. That's what happens in fact. But of course, for our for easy remembrance, we can imagine that this goes over to that side, and in that process the minuses become plus. Alright, so if we now do this addition, I hope I have done it correctly. If anything goes wrong, we can rectify. I mean, I do remember the final answer. I do not, however, have the solution done here with me. So this becomes what? 8, 18. Okay, so this becomes 18. Maybe it is 18, I guess we will see until we get to the final answer. Now, what have we found here? We next need to understand that. And for that, let us take the help of Venn diagram. Let us draw the situation. So this is our U. U is always there outside, and you have the 3 sets. Okay, so say this is F, B, and the cricket players, C. Alright. Now this set, for example, F intersection B is the intersection of F and B, that region. Okay. Similarly, B intersection C is this region, and C intersection F is this region. Note that the regions themselves, even these intersections themselves have their own intersection, namely the region where we have football players, basketball players and cricket players together. Any member that is lying in this region has played all the three sports and got medals. Okay. In fact, that's what we are considering, right? Simply playing the sports is not, that's not the sets we are considering here, but those that got medals in these sports. So let us give names to the number of elements in those parts alone. We may call the number of elements in that part alone A, the number of elements in this part alone B, and this part alone C, and let D be the number of elements or the number of players who got medals in three sports. We need to, however, write these things. Let A men got medals in football and basketball only. Well, to make it more clear, let's write like this, but not cricket. B men got medals in football and cricket, but not basketball. And C men got medals in basketball and cricket, but not football, not in football. Also, let D men got medals in all the three sports, i.e. D is equal to 3. We know D. However, we do not really know A, B or C. We do, however, know something else. We know that when we add A and D up, A plus D is N of F intersection B. Because F intersection B is this region, so this consists of those men who got medal in football and basketball but not cricket, and also those men who got medals in the three. So A plus D is this. Similarly, B plus D is this, and C plus D is this. We note that N of F intersection B is A plus D. N of B intersection C, B intersection C is C plus D and n of C intersection F is B plus D. So you substitute these things in this equation and this sum is how much? 18. Hence, A plus D plus B plus D plus C plus D is equal to 18. Alright. So this means what? A plus B plus C plus 3D is equal to 18. Let me keep the figure for now. And from this we are getting what? A plus B plus C is 18 minus 3D. 18 minus 3 times 3, that is 18 minus 9. So A plus B plus C is 9. Is this the thing that we wanted to find? Yes, because we wanted to find the number of men who got medals in exactly 2 of the sports. However, it was not mentioned which 2 of the sports. So all the all the possibilities have to be considered. A number of men got medals in exactly football and basketball but not cricket. B of them got medals in exactly football and cricket but not basketball, and C of them got medals in exactly basketball and cricket but not football. So their sum should be equal to the number of men who got medals in exactly 2 sports but not the third one. Hence, 9 men got medals in exactly 2 of the sports. And is the final answer 9, I hope? Yeah, yes. Yeah, that means not only is my calculation correct, but my guess is also correct. It is 58. And that just completes the miscellaneous examples. After this, we have the miscellaneous exercises, which are the last things in set theory. That, of course, we will do in the community section. So tonight I stop here itself. See you in the next upload. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.